All right. Hello, everybody. Welcome to the second pre-noon, I would say it's not morning anymore, session of our workshop. In this session, we have speakers from here from the University of Pennsylvania. And we will start with Alex Robey, who will present his work with Hamed Hassani and George Papas. George's group has won several awards during the last years, and they have also co-founded the series of the conferences on learning for dynamics and control, the L4DC. Alex will talk about his very new result on model-based robust deep learning. Alex, go ahead.
Thanks, Kostas. Yeah, so the title today is model-based robust deep learning, and the problems that we're going to be thinking about are how to exploit different structures in data to generalize to natural out-of-distribution data shifts. So I'm going to start by just saying a word about the kinds of applications that we're interested in tackling in this work. And in particular, I'm going to talk about what I call safety critical applications. What I mean by safety critical is any application in which the decisions made by a deep learning system impact the well-being of nearby humans. So canonical examples of this include something like autonomous vehicles, or robotics, or medical imaging, where in this last case, the detections or recommendations of something like a medical recommendation system might impact the care that a patient receives. So the high-level theme of this is that when we go to deploy deep learning in these kinds of safety-critical applications, it's essential that deep learning is robust to what I'm going to call natural conditions. So throughout this talk, I'm going to be talking about what I mean by these kinds of natural conditions. But before I move on to that, I'm just going to start by saying a word about adversarial examples, because that's going to motivate where I'm going with all of this. So when we think about adversarial examples, we usually think about our data points as lying in some Euclidean space, RD. So this image of the panda would be just some point in RD. And to create an adversarial example, we take this image X, we add some very small norm-bounded perturbation to X, and we create a new image, X prime, that's just a perturbed copy of our original image. And we call this new image X prime an adversarial example if the original image X is classified correctly by some deep network, and the generated or perturbed image is classified as anything other than the true label. So in this case, the original image might be classified as panda, and the perturbed copy might be classified as something like a gibbon. And so what we see in this kind of community of adversarial robustness is that adding small amounts of noise to your data can cause often kind of very poor performance. And what we've seen in the last few years is that since these adversarial examples were kind of discovered, there's been several thousand papers written on this topic of how to provide robustness against these norm-bounded shifts. And so we've really seen on a community level, researchers really caring about this problem of robustness in deep learning, which has been really good to see. But of course, given that most of the focus in this community has focused on norm-bounded perturbations, a natural question that you might follow up with is, well, are there other kinds of transformations that cause misclassification in deep learning? And of course, the answer to this question is yes. So we've already seen these norm-bounded perturbations. But what has been shown in the last few years is that things like spatial transformations, like rotations, out of distribution shifts, something like adversarial patches or adding graffiti to data can cause poor performance, as well as what sensing mechanism you use to capture your data can also drastically change the performance of your algorithms. And finally, there's this notion of natural variation that comes up again, or at a high level, this should capture kind of the ways that data varies in the kind of environments that you might encounter in safety critical applications. And so it's actually these kinds of natural variation, which I'll talk about more throughout this talk, and contrast them with the kind of more studied problem of adversarial examples. So in the applications that we care about, these safety critical applications, the question comes up, well, how does data actually vary in the environments that we're interacting with? So for example, we might have the following task. We might have a data set of images of street signs taken during the day in plain sunny weather. And our job might be to design a deep learning system to correctly classify this sign in a given image. And of course, this is a fairly straightforward problem if we're going to train on sunny images taken during the day and then test on kind of IID images from the same distribution. But the problem is when we're interacting in a natural environment, we might not always see these sunny conditions. So we might see something like snow in the image. And this is something that can clearly, change the classification of our deep learning system. But of course, snow isn't the only way that data can vary in these natural environments. So we might also see something like rain in our images, or a dirty camera lens, or darkness, or fog, or blurring, or grayscale, or exposure. So this is all to say that as opposed to the case of adversarial examples where data kind of only varies according to a very particular norm-bounded additive perturbation, in natural environments, you're very likely to encounter different kinds of variation along all of these different axes. And so it turns out to be a much more kind of less well-posed problem than the case of adversarial examples. So given that all of this research and all of these improvements and advances have been put into the problem of adversarial examples, and this whole robustness community has kind of been born out of it, you might think, well, is there a way that we can use all of these advances in the adversarial robustness community to tackle this kind of concomitant problem of natural variation and providing robustness to it? And I'm going to identify two challenges to extending ideas from adversarial robustness to natural variation. And the first challenge that I'll identify is the modeling challenge. So again, whereas in adversarial examples, the perturbation is always being generated in the same way, it's not always clear how, in the case of natural variation, I would select a function that can say take an image in daylight and transform it to a corresponding image with kind of snowy conditions. And similarly, I might want to do this for the dirty camera lens or the rainy image. So again, a priori, it's not clear how to select a function that can model this transformation from, say, one domain to the other. And what kind of goes along with this question is, well, if we were able to model these kinds of transformations and capture the dynamics of how data varies in natural environments, we then need to be able to exploit this knowledge of the dynamics of, say, weather conditions or lighting to devise new algorithms that can improve robustness to these kinds of transformations. So these are the two challenges that I'm going to talk about in the rest of this talk, and how we kind of formed our solution to these two challenges in our paper. So to start, let's talk about this modeling challenge. How do I capture the dynamics of natural variation? What I'm going to propose is a simple solution. I'm not going to claim that it's the optimal solution, but this is certainly something that we will show works very well in this setting. So I'm going to introduce what I call a model of natural variation. And all this is just a function g that takes two arguments, x and delta, where x is something like your input data, like images, and delta is what we call a nuisance parameter. You can think about this as just a low dimensional vector, say in R2. And the idea with these models of natural variation is I'm going to pass these two inputs through the model, and I'm going to get a new image at the output that has a different level of natural variation than the input. And then if I were to change this nuisance parameter delta, the goal is that this function will be able to output a new image that has a different level of natural variation than the one that was generated with the previous delta. And so if I repeat this process again, the ideal situation is that we get yet another image with kind of a different level of snow in this case. So ideally, this function, this model of natural variation g, will have the property that by varying delta, we can produce images with different levels of natural variation. Now, keep in mind that I haven't said anything about how you actually obtain this. I'm just trying to introduce kind of what the ideal case is here with these models of natural variation. So let's take a closer look at what this means. So again, we have this input image X. We have a model of natural variation, say the same one from the previous slide with snow. I'm going to define a set called the learned image manifold. And this set just contains all of the images in our data space, RD, that can be obtained by passing the original input image at the top of the screen X and some vector delta through our model of natural variation. And this set is going to look something like a manifold in our data space, RD. And each point on this manifold is going to correspond to an image that has a different level of natural variation. So as you can see, as I move along this manifold, all of these different points have images with different levels of natural variation. And this picture should kind of stand in comparison to the much simpler geometric perspective that we get with adversarial examples. So in that case, we kind of have these norm-bounded perturbation acting in these epsilon balls around our data points. And now the geometry that's being induced by this model of natural variation is in some sense much more complicated. And so what we're going to do is we're going to exploit this geometric intuition to formulate an algorithm that can use a model of natural variation to provide robustness against the form of natural variation that's captured by this model G. So again, we're just assuming that this ideal model G is known a priori. And we're going to consider the following optimization problem. So notice that it's a min-max problem where the outer min problem is over some weights of a neural network W. And this inner maximization problem is over the space of deltas for our model of natural variation. And to explain what's going on here, I'm actually going to split this up into two pieces. So let's first consider this inner optimization problem. Now, given a loss functional L, which takes 3 arguments, in input data, like an image, a label, and the current weight of a neural network, the idea in this problem is going to be for a fixed image, I want to search over my model of natural variation in the nuisance space to find a corresponding output image that gives high loss on our current model. So by searching over this space of deltas, again, we're looking for an image, G of X comma delta star, that will have very challenging natural conditions to classify. So again, relying on our geometric intuition here, the idea is that by looking at first delta 1, then delta 2, then delta 3, we're trying to find an image passed through our model of natural variation that is quite challenging to classify. And now considering this inner maximization problem, we can rewrite our outer problem with this solution delta star. And now after rewriting this problem, it actually becomes kind of something that may look very familiar to you. It's just kind of an empirical risk minimization problem where instead of classifying the original data, we're classifying this challenging data point G of X comma delta star. And ideally, at the end, after solving this optimization problem, we hope that the weight W star is robust against natural variation. So this optimization problem is kind of the central focus of our work and how we're choosing to deal with natural variation here. So with that, let's talk a little bit about how you actually solve this optimization problem, because again, this is kind of a non-concave, non-convex min-max problem. And we have to rely to some sort of approximate method to solving it. So in particular, we're going to propose 3 algorithms here. All of the algorithms are going to do alternating steps of solving the inner problem and the outer problem. And all of the algorithms are the same in one sense in that they solve the outer problem with just some standard first order SGD or something like this. And all the algorithms are going to differ in how we solve the inner maximization problem. So the first algorithm that we'll propose is what I call MRT, or model-based robust training. And the idea here is just I'm going to sample k different values of delta, and I'm going to choose among those sampled values the delta that causes G of X comma delta to give high loss under our current weight. So this is truly just a 0th order sampling-based approach to solving that inner max problem. The second approach is what I call model-based adversarial training. And here I'm going to perform k steps of gradient descent or ascent on the inner max problem. And this is more in line with kind of the algorithms that are derived in the adversarial robustness community like PGD, where I'm trying to exactly solve that inner max problem as best I can. And finally, the last algorithm that we have is called model-based data augmentation. And here, rather than explicitly solving the maximization problem, we're going to exploit this nuisance parameter delta, and we're just going to select k values of delta and generate new images that we just append to our data set and perform ERM. So this is truly just a data augmentation technique with our model of natural variation. Then the final thing that I'll address before I show just a few experiments is we've gone through this whole talk so far assuming that a suitable model of natural variation exists. And I'm going to spend one slide just telling you a little bit about how we were able to learn models of natural variation in our paper. So recall, this is the optimization we want. And this g of x comma delta is kind of the central thing that we're now focused on finding. I'm going to split the kinds of models that we can learn into two classes. So on the one hand, there are known models, and on the other, there are learned models. So let's start with known models. You could think of the class of known models as any sort of function that's known a priori that you would want to provide robustness or invariance to. So for example, notice that if I replace g with x plus delta, I recover the well-known formulation of an algorithm like PGD. Or if I wanted to provide robustness against rotation, I could just replace g with a rotation matrix times my data. And finally, you could imagine exploiting other kinds of knowledge or symmetries that you would want to provide invariance against in this spot of G. So that's the class of known models. The perhaps more interesting case, at least for the purposes of our results, is the class of learned models. And this is for anything like weather or lighting or contrast, where it's not known a priori how to transform data according to, say, the dynamics of snow or something like this. So in cases like this, we're going to propose learning a model of natural variation using unsupervised and unpaired image-to-image translation networks. And the idea here is that given an image X and some nuisance space delta, under the hood of this model of natural variation, we're going to have this image-to-image translation network, which is just learning from unpaired and in an unsupervised way how to learn this correspondence. And by using this kind of recent, generative modeling technique, we can produce these output image or this distribution of output images that really captures kind of, for example, here, changes in lighting. So I'm happy to talk more about this offline because there's actually a lot going on with how we do this model of natural variation, how we learn it. But for now, this is all you need to know for the purposes of our results. So let's consider a first experiment here. And I'm going to start by considering an experiment that's quite similar to a lot of the things that are done in the domain adaptation literature. So in particular, I'm going to take a source domain where I have labels and I have images. And I'm going to consider the distribution shift from this source domain to a target domain where I only have, say, images and no labels. And so to do this, I'm going to consider kind of three approaches: a vanilla standard empirical risk minimization, PGD, which is one of the state-of-the-art adversarial training methods, and ADA, or adversarial discriminative domain adaptation, which, as the name suggests, is a domain adaptation technique. And we're going to compare these approaches to our model-based approaches from a couple of slides ago. And keep in mind here that all of the baselines and our methods have access to the same labeled data. And so the goal here with our model-based algorithms is to learn a model of natural variation from these unlabeled images that can allow us to use our algorithm in this case. And what we find is that when we learn this model of natural variation and solve the optimization problem that we had a couple of slides ago, that we're able to fairly significantly improve over both the kind of vanilla baselines and the targeted ones like PGD and domain adaptation. So another kind of interesting experiment that we—
Alex, sorry, 2 minutes.
2 minutes? Yeah, I have 2 more slides, I think, yeah. So another interesting experiment where domain adaptation doesn't even necessarily apply is when we have multiple shifts in our data distribution. So for example, we could have a shift in contrast, and we could have a shift in brightness. But we might not have data corresponding to both a shift in contrast and a shift in brightness that we can train on. The advantage to using the model-based technique is that you can learn two separate models of natural variation, one for contrast and one for brightness, and then by composing them together, you can create a new model that will allow you to provide robustness against the combination of both changes in brightness and changes in contrast. So you can see our three methods are here at the top, improving about 20% over the baselines that had the same data. Another variant of this is, well, a natural question that you might ask is, well, if I learn a model on one data set, like this going from MNIST with blue backgrounds to MNIST with red backgrounds, is it possible to use this model, which was learned offline, on other data sets? And it turns out that it is quite possible. So we applied a model, this one learned on MNIST, to 5 new data sets. And you can see that despite the fact that the model hasn't seen these objects in training, it's still very effectively able to change the background colors. And what this means is that we can use and reuse models that were trained on different data sets to provide robustness against this change in background colors on completely unseen data sets during the training of the model. And finally, the experiment that I'm going to end with is kind of our most recent result. And this is robustness from a data set, a very high dimensional data set like ImageNet, on the shift to something like ImageNet-C, which gives kind of common corruptions to the image. Here you can see it's a snow corruption. What we're going to do is we're going to train a model of natural variation using unlabeled data from just 5 classes of ImageNet. And then we're going to take 50 new classes and apply our model of natural variation on these to train classifiers for these new classes. And what we find is when we do the baseline approach, just the empirical risk minimization, we achieve about kind of 20% and 40% on this snow and contrast challenges. And when we apply our model-based techniques, we can achieve significant improvements in the robustness on this shift from, say, images in daylight to images in snow. And so the final takeaway message here is that the methods that we're proposing in this paper allow you to exploit symmetries and structures in data to provide natural outer distribution robustness. And with that, I just want to say thanks, and any questions if anyone has any.
Thank you very much, Alex. It's really very exciting. There is a question by Kevin. Can we train a VAE between with x2 is equal VAE of x, with x2 being the natural variation? I think you can even go back to your slides, which it is an decoder encoder, what you showed.
Yeah, so if I can just go back here. Let's get through this. Should be here, yeah. Yeah, so this, I mean, the architecture underlying all of this is essentially just a couple of GANs coupled with a variational autoencoder. So there's actually a lot of different ways that you could think about learning this model of natural variation, all of which might make sense. And so that's why I'm kind of claiming that we're not saying that this is the optimal way of learning this model. You could certainly consider putting a variational autoencoder and seeing how that would work here. So the point is just that you can learn any sort of model here offline, any sort of G that you might want to use, and then you can plug it in here to this optimization procedure.
The second question by Sinan Kaplan is, do you take into account region-based natural variations in an image? For instance, in the sample image you showed the traffic sign, let's say there was a fire and some part of the forest was gone. Is there any way to have more local variation?
This certainly isn't something that we've explored yet. I mean, again, this would depend on the kind of generative model that you're interested in. So if you could, you know, find a generative model that can kind of exploit or produce this kind of local change, then that's also something that you could certainly use in this optimization. But that's not something that we've looked at. That's quite an interesting direction, though, I think.
All right, thank you. Okay, there is, let's take one more. could you talk a bit about how to choose the perturbation set delta for the more complicated learned models?
Yeah, that's a great question. So we just did, in the paper, we just did some hyperparameter tuning on how large to make this perturbation set. So for all of the perturbation sets in our paper, there were just some subset of R2 centered at the origin. So for example, this one that you can see here on the slide was just the unit square between -1 and 1. So the idea is just to select that perturbation radius either by some hyperparameter tuning or just visually to find a region that captures the natural variation that you care about. So again, this is something that you could explore more in depth about what actually the best way to choose this perturbation set is and what dimensionality you might want to use. In this case, we're sticking to R2 just because it allows us to visualize the natural variation that we're capturing, but you could consider all kinds of perturbation sets here.
All right, thank you, Alex. Our